Dari, hello. It's the middle of May 2021 and today we're going to look at booting a Cromemco Cromix system. Now this video is designed to complement another YouTube video I previously shot, which was a visual interpretation of how a Cromemco system boots. And by system I mean a system that's got a combined Z80 and 68000 processor. Going back into the history of it, Cromemco systems first came with the Z80 processor, but then they thought that the industry was moving towards 68000, Motorola 68000 processors, so they produced a card which had both a Z80 and a 68000 on it, which was exceptional in the sense that you could run all the Z80 programs you previously used to run on the CP/M and CDOS operating systems, but also you could write 68000 assembler or C and various other languages programs and run those as well. So you had the best of both worlds. It's now 2021 and MFM hard drives, which were expensive in the day, are now not quite as expensive but impossible to find. So the first section of this video, which is this bit now, is going to talk about David Geswine's magical, wonderful, can't speak highly enough about it, MFM hard drive emulator. So using a small BeagleBone Black Linux-based computer running Debian and some hardware, the combination is used to simulate up to 2 MFM hard drives. So first of all I'm going to show you that, because we need that to be able to boot the computer, because these systems in the early 80s were not very useful without a hard drive. And at the time hard drives were super expensive, but after the sticker shock of about $3,000 for an 11 megabyte drive, which was the first Cromemco sold effort, which is an IMI drive and a specialized controller, things got a bit less expensive because companies like Seagate came onto the marketplace with the MFM hard drive interface, or the Seagate SC506 it was called, hard drive interface, and a lot of vendors including Cromemco used that interface in their later computers. So the IMI 11 megabyte drive was out, the Seagate drives were in, and for that you needed a hard drive controller, which is the ST-DC hard drive controller, and that's what I've got on the system that's running. So first thing we're going to do is we are going to start the emulator, and let's give that a go. I've got a command line I think already in the pipeline. So here we are. I've got the command. This is running on David's emulator product. We're running full Linux, and we're going to start the emulator with 2 drives. We're going to use the first drive here, which is my master hard drive, and the second one, which is going to be a drive that we're going to initialize for the first time. So we're going to start that up. There'll be more to say about David's emulator in other videos dedicated to it, but let's just hit enter and let's start the emulation. Right, so now we've got the emulation running. You see the first drive of this form factor is up. The second drive with this number of cylinders and tracks is up. Move that window out of the way, and now we're going to be back to the Cromemco system, which was previously shut down. So I'm going to restart it. 1 second. Okay, so now I've just powered the system off and powered it back on again. And this system is set on the diskette controller, which has got the serial interface to which this COM port is attached, to auto baud. So I'm going to hit enter a few times, and you've got the RDOS, Resident Disk Operating System Monitor version 3.12. So when you hit enter, the CPU, the Cromemco system has started. It's jumped to location C000. That's the ROM on the diskette controller. And that ROM's first interaction is to try and listen on the serial port on that card and wait because it's set to auto baud. It's waiting to find a carriage return, and as you hit carriage return multiple times, it's looking out for that. It tries different baud rates until it finds the right one, and when it finds the right one, it prints out that message, and it's also set to auto boot when it finds that, so it's going to try and auto boot. So that's why it said that. I've interrupted the boot because I want to show you how to boot from a specific hard drive. And generally speaking, even the latest floppy disk controllers, it was difficult to get it to boot to the right hard drive, so people would always break out. So if I want to boot the system, I would say B, where are we? Oh, sorry, the keyboard is not working well. Right, we're back. I'm going to say B ST0, which means boot the 0th, the first partition on the drive. We'll look at how hard drives are organised briefly once we've done the initialisation of the second drive. So here we go. Memory test for the first 64K memory. Attempting to boot. Standby. Once you see the standby, you know something's working. Standby is a message coming from the actual boot block. So when you get the message standby, you know it's gone to the hard drive, you know it's read the boot block, you know it's executing the boot block. Okay, so as my previous YouTube video was trying to show you, you type BST0, this is, you're interacting with the floppy disk controller ROM, but the floppy disk controller ROM has some code in it which knows about the hard drive controller, the STDC hard drive controller. So that command will go to that hard drive controller and extract the boot block from the bootable area of that hard drive, of that partition 0. And the thing that the program does first is a better memory test. Now you saw here you were doing a memory test of 64K, but here we're doing a memory test of all the memory in the system. Now this boot block is configurable actually, so it's not just this is part of Cromix.sys, and it's not just the actual area which is sorry, I'm not saying it very well. This menu is selectable, and the reason why we're only setting this amount of memory is because we've previously generated the operating system to deal with this amount of memory. Okay, so at this point when you've got standby, it's read the boot block. At this point here, it's actually read Cromix.sys, because Cromix.sys is actually what's got this address and memory test inside of it. So now, although you've read the full operating system and you've done an extended memory test, you could actually boot to anywhere, to any other partition. But we want to boot to the partition on this controller, 6, and we want to boot to the 0th partition, which is where we got this program from in the first place. And then we've got a boot. So I've handcrafted the operating system so it comes up with a little message. Log in the system. I've removed the passwords, and I've removed the passwords because, of course, if you were to download this image from GitHub and use it yourself, you'd need to know what the password is, and that all gets very complicated. So the passwords have been removed. Right, we're now up and running. However, this system was never supposed to run in the year past 2000, so I'm going to do a time -s to set the clock to be absolutely sure things are right. We're in month 5. We're in the 18th of May, and we're in year 121, as you know, added from. So we're only expecting to get up to 1999. So that's set the year correctly, and let's do the time, which is 1927. Okay, right. So now we're up and running. We can do stuff like ls -l of the root file system. You can see we're up and running. And what we're going to do next is we're going to format that second disk that we mounted. So again, both of these hard drives are synthetic drives, and again for 2021 that's good for reliability. So we're going to do an init hard minus n. And the importance of the minus n is that it isn't going to look on that second drive and think, ooh, has this drive been formatted before? So logically it should totally ignore any data that, or any kind of binary pattern that's on that drive. I think it helps working on the system. Let's see if we can do h of init hard. Let's see what it says. Yeah, minus n for new disk. The init hard utility initializes hard drives, etc. Right, let's go back. Init hard minus n. Now, as I described in the previous video, SDDC disk controller can take up to 2 disks. Each disk can have a number of partitions, but there's a special STD number which relates to the whole drive itself, and we need to tell the program about the whole drive so it can go and partition that drive. So the first whole drive is called STD31 and the second whole drive is called STD63. So let's go for STD63, and that's referring to the second hard drive, which is blank, and we're going to format it and then make a file system on it. So now we have to remember what the geometry was that we were emulating. So remember, it was going to be 16 surfaces and 50 tracks. Right, so on a physical hard drive, hopefully never a digital hard drive, you had the concept of alternative tracks, meaning that over time, or at point of sale, even when you bought the drive first hand, the drive might contain some defects. And where would you want to put the remapped defects? So you might buy a drive in 1980 and it says on track 1, or sorry, let's say track 10, sector 1, there's a problem. So the idea is that you'd have an alternate track table, and in this case the operating system is manually going to remap that. So if you have an alternate track table on track 100, not a good example, we've only got 50 tracks, on track 50, then we could say, well, instead of going to track 5 sector 1, we know that's damaged, we're going to go to track 50 sector 1, it's going to remap that track. So Cromemco didn't use sectors for the hard drive controller, they used tracks. So if any part of any surface of any track was damaged, you'd have to lose the whole track. That's what's called an alternative track area, not an alternative sector area. Now we're using a digital emulator, so these things, quotes, can't happen. But obviously the Cromemco system doesn't realise that, so number of alternative tracks can be 0. Starting cylinder of the hard drive. Well, the convention is we start the drive, the starting cylinder is track 1, not track 0. So we're going to leave that option. And the right pre-comp. So in the olden days, as the physical head used to travel across the drive, the magnetic density could be changed because you needed a slightly different density as you wandered across the disk. Again, this is a digital system. This completely does not apply. 50. Now I'm going to say yes to this. So this is going to be the world's most boring video because it's going to need, unless my partner is managing to edit it. So if that's the case, you'll see in a second. We do want to initialize some tracks. The first cylinder is going to be 0. The last cylinder is going to be 49. That's 50 tracks in total. The first head is 0. The last head is 15. That's all correct. And now we're off. Now, at this point, hopefully there's going to be some lovely editing going on. By the way, I can show you the window, and that's the window of the hard drive emulator, and you can see it seeking, and you can see it selecting the different tracks. You see, moving from track 17 to 18, 18 to 19. You can see it seeking. That's the sort of status screen of the emulator. Again, it's the wonderful David Guess-Wine emulator. There will be links, there will be all sorts of plaudits sooner or later. What a wonderful device. Actually, we've nearly finished, so I think my waffling has come to the forte. Let's go back to that interesting screen so you don't get too bored. Come on, track 40. Track 40. 10 more to go. (43). There are limits to how many tracks and surfaces you can have, but the master disc, which is 1500 cylinders in size, is considerably bigger. Right, do we want to change the partition table? We're going to say yes to that. So we can divide that physical hard drive into one or more partitions. So I'm going to say the first partition, how many cylinders do I want to have? I'm going to say 20. Second partition, partition number 1, counting from 0, I'm going to leave it at 29. So we're going to build a disk with 2 partitions on it. Alternate track location, well, I always put that at the end of the drive. I don't know why I put it at the beginning. I just don't know. So we're going to put that at the end. 49. Do you want to add an alternate track? No, I definitely do not want to add an alternate track. No. So we're finished. Now, let's do a disk info of the drive. STD. Remember, you've got to refer to the whole drive. There you have it. So this is a summary of that second hard drive. You can see I created on that drive 2 partitions. The first one's a whopping 3.2 megabytes. The second partition is a 4.6 megabyte partition, and in total that's 8 megabytes. Now it's pretty decent size, really, for the day. For the 1980s, if I bought say a 10 megabyte hard drive, I might expect to pay a couple of £100 for such a device, say £300 or £400 in 1980. Let's say 1981/2. Yeah, that's what we would get. Now, there's no Unix or there's no Cromemco file system on here, so we need to make a file system on that drive. So let's do that. So make file system std. Now, this is a second drive. The second drive starts at 32. Okay, so it starts at std 32, 33, 34, etc. So we're going to make a file system on std 32. And let's see what it's really doing under the covers. Here's the emulator screen. You can see it's seeking. Quite fascinating. Seeking different tracks. Okay, it's writing. It's done it. So now it's formatted correctly. Initially, the file system has been made. I can do things like free std32. I'll show you how much free space is remaining on the disk. Formatted free space. And I can do a check of std32. So this will check. Check is a shortcut for I check then D check. Cromix had a very basic scripting language, like you might have in early DOS, a batch programming language, very similar. So it's first of all done a directory check here, and then it's going to do an I check, an inode check, which is a bit more horsepower, takes a while. Again, you can see it seeking here. So now we see that we have this wonderfully, beautifully formatted. There are no blocks missing, there are no bad free blocks, there are no duplicate blocks, there are basically, if all this is 0, there's no problems with that drive. So if we ls-l of root, I've got a /z there, so I can do a mount of std32 onto /z. or Z for our American listeners. So I'll just finally, I know I'm labouring a bit, but let's just copy some files on there just because we can. So go into the bin directory. CD. Oh no, it's not CD, it's D. CTO. So there's a directory of files. It contains a few files. I'm going to use the cptree command to copy those files. But I'll just quickly show you that if I do config of /bin/cptree/bin, you'll see that the allocated memory is an enormous, and I mean that seriously, 256k bytes. So that means when this program starts up, it's going to request 256k bytes of memory, which is quite a lot. I think when the operating ships standard, I think cptree gets 16k. That's the but the bigger memory size you give here, the faster the copy is going to be. So let's do cptree minus force time verbose, the current directory, to /z. Let's go. Done. Can I type sync? I can on this level of the operating system, just paranoid there. And let's do an unmount of std. Oh, no, let's have a look first to prove it's done it. ls-l/z. There you go. Oh, look, it's preserved all the dates and times. How wonderful. 1983. It's been a bit of a struggle to keep these dates and times as accurate, because if you start to copy files around on most modern operating systems, you lose the dates and times, and you get the date you copied the file, not the date the file was actually originated. Anyway, I've got the originals. Right, so unmount/z. That's wrong. Unmount by the device name, std32. And we're going to do a check. Shortcut I check of std32. So we're going to check that disk again. We're expecting it to be clean. I've unmounted it. Didn't make any errors, haven't misbehaved it in any way. And blocks used in files. So previously, you see, that wasn't a zero number. There's one directory, and there's 177 blocks, and there are 9 ordinary files. That's it. So go back to the root directory, shut down the operating system. This is the way that I use, it's the quickest way. It kills the processes. So let's just have a quick look. ps-al. So there's a process that is there's a process that runs the whole computer, p_1. So if I kill that process, I will basically shut the computer down gracefully. It's off. So now I'll show you the emulator screen. So I'm going to just physically switch off. No, I'm going to break out the emulator. At this point, if I switch off the computer, I could send a bad signal through the cables to the emulator and corrupt the disk. So the best thing to do now is press Ctrl+C on the emulator screen. Okay, we're now back to the emulator screen. I can do it. I can shut that down. Ooh. That shuts down the BeagleBone Linux computer, which provides the hard drive support. Hit enter a few times, it'll probably disappear because it'll go. Yeah, it's dead. So I can close that window. We're back to the Cromemco window, and now I can switch off the computer. So what have I shown you? I've tried to show you that there's a wonderful MFM hard drive emulator, of which there'll be more to talk and show you later. I've booted the Cromemco system. It started off with the Z80 processor. It read the Cromix.sys program, and then from that program you're allowed to do a boot of into any partition that you want. We booted the system. We logged in. You can set it to auto login, but it hasn't been configured that way. So we logged in as system. We went to the second drive. We initialized that drive. and then we split that that second drive into 2 partitions, and then we made a file system on the first partition on that second drive. Then we mounted it, copied some files onto it, unmounted it, and did another check, and all is well. Okay, so that's it for this video. Thanks for watching, and there shall be more Cromemco videos soon. Thanks.